Hello students, in last part we have seen little bit of free and forced solution. I have given homework to all of you. I hope that all of you have completed the homework. Okay. Now let's go to next topic of your syllabus, harmonics and overtone. So what exactly harmonics and overtone that we have to see? These are the words they have used for frequencies. Suppose any body is vibrating or oscillating with its own frequency, natural frequency, then that natural frequency is said to be harmonic, forced harmonic. The natural frequency of vibration of any body is said to be forced harmonic. Let us suppose body is vibrating with the frequency F, and this F is what? Natural frequency. Natural frequency of vibration of the body. Body is vibrating with this natural frequency F, then this F is also said to be the basic frequency of vibration, that is nothing but a fundamental frequency. Fundamental frequency of vibration, and this itself is said to be the forced harmonic. It is said to be forced harmonic. And all other frequencies which are integral multiple of this F, twice F, thrice F, 4F, so on. All these are the frequencies which are greater than F. All these are the frequencies greater than the fundamental frequency. These all other higher frequencies which are integral multiple of fundamental frequency, the higher frequencies are said to be harmonics. This is said to be second harmonic. This is said to be third harmonic. This is said to be fourth harmonic. In this fashion, all the higher frequencies are said to be fifth harmonic, sixth harmonic. So in short, harmonic is nothing but what? The frequencies higher than the fundamental frequency which are integral multiple of fundamental frequency. Twice F, thrice F, 4F and so on. The fundamental frequency itself, this is said to be forced harmonic. Then second higher frequency is said to be second harmonic. Third higher frequency is said to be third harmonic and so on. So these are said to be the harmonics. If you got it, it's well and good. If you don't get it, don't worry. In the next subsequent topic, we are going to learn this. But you must remember that the basic natural frequency of vibration of body is said to be fundamental frequency, and the fundamental frequency itself is said to be what? It is harmonic, first harmonic fundamental frequency. Next higher frequency than the fundamental is said to be second harmonic. Next higher is said to be third harmonic and so on. So these are the higher frequencies. Okay. Now let's go to overtone. Might be all of you are well known about the word tone. Overtone. Over means large tone. If someone get angry while doing something, or suppose something get occurred so that person get angered. So in that case, the tone of that person get changed. Normal tone is different, and that person started speaking with a large, louder voice, that we can say that this tone is increased. That is said to be overtone. So what exactly overtones are? Nothing but so these are, overtone means what? All the frequencies higher than the fundamental frequency, all the frequency higher than the fundamental frequency which actually exist in the sound, are said to be overtones. Again, these are the frequencies. Then suppose we have drawn F as a fundamental frequency, as though it is said to be zeroth harmonic. Okay, zeroth harmonic. Then let's see, F1 is a higher frequency, first higher frequency and the fundamental frequency. And this F1 equal to what? F1 equal to what? Suppose it is twice N or twice F1. Twice F1. First higher frequency, twice F1. Okay. Then this is said to be first harmonic. This is said to be second overtone. First harmonic, second overtone. Fundamental frequency is zeroth harmonic. First higher frequency than the fundamental is said to be first harmonic, second overtone. Similarly, another frequency F2 greater than F, if it is equal to thrice F2, if it is equal to thrice F2, or it is thrice F, we can say. So it is thrice F. In that case, this is said to be second harmonic and third overtone. So in this fashion, as the frequency increases, this first thing is nothing but harmonic, 2 means second harmonic, thrice F, 3 times the fundamental frequency, so 3 times higher than the fundamental, that is said to be overtones. So these are nothing but harmonics and overtone which are present in a sound. Now if you got it, it's well and good. If you didn't get, don't worry. We are going to learn the same in the next subsequent topic. There actually we have to derive the equation, and while deriving that equation you get whole idea about this harmonics and overtone. Apart from this, let's, in your book they have mentioned somewhere, so suppose harmonic is used when the frequency of particular overtone is integral multiple, so that term they have used. Then apart from this, but all harmonic may not be present in the given sound. See, harmonic may be present in the sound, may not be present in the sound, but overtones are always present in the sound. Higher frequencies than the fundamental frequencies are integral multiple of fundamental frequency are said to be overtones. Overtones are always present in the sound, while the harmonic, some cases harmonic may be present, all harmonics are present, in some of cases even harmonics are present, in some of cases odd harmonics are present. I know that you didn't get it. You didn't get the odd harmonic, all harmonic are present. Don't worry, that we will see in the next topic. Let's go further. The next topic is end correction. Now this end correction means what? That we have to consider. Basically, you should consider it later on, but according to the book, they have taken first, so we'll go according to the book. So it is end correction. So to correct this or to understand this end correction, first of all, it is very essential to learn what is said to be end correction. Now see, the simple example we will consider, suppose we have the tap, or suppose this is the pipe. This is a pipe which carries some water somewhere, or suppose it is coming from some tank. So here overhead tank, so this is water tank, and from this tank, suppose this pipe is connected, and this here there is some cork, suppose here, suppose there is tap. So this is suppose tap, T is a tap. So we can close and open this pipe here. Suppose this is in off condition initially. Suppose this is off. No water is coming out. No water is coming out. Definitely there is water in the tank. So there must be water in the tank. And suppose this cork is off condition. In that case, the water get coagulate here. It can't come outside. But when we start, when we on the cork, you can see we have the pipe up to this part. This is the end of the pipe. So when we start the cork, it is seen that water must get fall down from here in downward direction. In on condition of the cork, water must get fall down like this. Okay, because there is the end of pipe. But practical situations are such that when we switch on the cork, it is seen that water can't fall here. The water little bit goes forward and then little bit goes straight line forward like this, and then it will fall here. Now remember, here there is no pipe. Still, why here there is no pipe? Pipe ends here. Still water goes little bit ahead, then fall down. What does it means? Actually, we are saying this is the end of the pipe. But remember, because of the force and pressure exerted by water, water can't fall down here like this. It goes little bit this much distance ahead of the end, and then it will fall down. And this distance is said to be end correction. This distance is said to be end correction. We have measured the length of the pipe up to this. Up to this we have measured. But actually it is seen that water fall down little bit ahead of this. So this thing we have not taken into consideration. And if you consider that end correction, that is said to be end correction, because at the end this would be the error. That's why it is said to be correction at the end. That is nothing but an end correction. That might be taken into account while doing the calculation. Otherwise, if we assume the length of the pipe up to this, it is small l, suppose. Length of the pipe up to this is small l, suppose. Now here, this is what? Suppose this is represented by, this distance is represented by small e. So if we do the calculation by taking this length, there would be error of this. So that you must consider the total length equal to this l plus this end correction e. and that we have to consider in this topic. That is nothing but a end correction. So this I have told you by taking a simple example of water and the pipe. Now same thing you can apply here in end correction. This concept can be applied for the two cases. First is a pipe. First is a pipe open at one end, and close at other end. In that situation, what is the case that we have to consider? This is the first case when pipe is open at one end, close at other end. And the second case is what? Second case is here like this. Did you got it? Yes. Second case is the pipe open at both the end. So these are the two cases according to the end correction get changed. So first of all, let's go to this. What is pipe open at one end? So this might be the pipe open at one end and close at other end. Let us draw it. So you can draw this pipe. Here this is a close end, you can say. The pipe close at this bottom and it is open at the top. So this is said to be pipe close at one end, open at other end. What get occur? So see, there is one conditions. There are boundary conditions. When some wave get passed through this, it goes to the bottom and again it get reflected. So this is incident wave, this is reflected wave. Incident wave, reflected wave. It little bit goes ahead of this. Suppose this is the length, we have measured length of the pipe is this much, and that length measured is small l. Small l is the length of the pipe. But actually it is seen that when wave incident from this end, actually it is not incident on the end, little bit above. It incident here at the bottom, and when reflected wave goes, it can't come here. It goes little bit above this. And suppose this above distance is nothing but a E, and that we want to determine, and that is said to be end correction. So what are the boundary conditions here? Antinode, the point of minimum displacement or zero displacement is stationary wave. This node, so not an antinode, it is a node. Point of minimum displacement, or we can say zero displacement. Node is always formed at close end. This is a boundary condition. And at the same time, another condition, the particle where displacement is maximum, amplitude is maximum, it is always formed at here, this point. This is said to be antinode. So this node is formed at the close end, antinode is formed at, so it is antinode is formed at open end, and node is always formed at close end. As condition says that antinode is always formed at open end, what does it means? The pipe which is open at one end and close at other end, it has end correction at this open end only. So this is E must be considered at open end only. Is that clear? Similarly, if we see here the pipe which get open at both end, I have drawn the pipe like this. So this pipe is open at the bottom as well as the pipe is open at the top. In this situation, pipe open at the bottom and the top. In this situation, again what will occur? As condition says that antinode is always formed at the open end, you can write it like this. So you can draw it like this. So this is the condition. So this should be the antinode, little bit goes ahead. This should be the antinode, little bit goes ahead. So these are the antinodes. This is the node according to boundary condition. But as this pipe is open at both ends, so the two correction you should take. So suppose we have taken this as length of the pipe as small l. Then here this would be the end correction at the top, it is E. Again same end correction should be there at the bottom, again it is E. So the end correction in the length is what? E plus E, it is twice E. Then what is length here? Total length is equal to L equal to small l length of the rod or pipe plus E, so it is plus twice E in case of pipe open at both ends. Here in case of pipe open at one end, what is the correction in length? L equal to small l plus E only, because correction at the top only. That is nothing but a basic difference of end correction in a pipe open at one end, close at other end, and the pipe open at both ends, it is double. Here it is single. That is the difference for this end correction. Now, according to one scientist, there is one scientist whose name is Reynolds. Reynolds says that if you find out this end connection in both the pipe, it comes to be represented by E, and it is equal to 0.3 times D. 0.3 times D according to Reynolds. This D is nothing but what? Inner diameter. Suppose this is the inner diameter of the tube. It is represented by D. So inner diameter of this tube or pipe is said to be D. So end correction is 0.3 times the D. Okay, 0.3 times the D. So that is nothing but a end correction that we must take into account, and that already we have learned. It is L plus twice E for a pipe open at both ends, L plus E for a pipe open at one end. So this is only the end correction we have seen. Now let's go further. Further, what we have to see? We have to consider the vibration of air column in a pipe. Air column vibration. What is air column vibration? When we try to sing some melodious sound by using flute, what we are going to do? We are going to blow the air in that small pipe which has some holes, and according to our fingers, pleasant voice can be created. So when we blow the air, some air particles are there, air gap is there in the pipe that start vibrating. So that is nothing but said to be air column. So let's say the first one, vibration of air column in a pipe close at one end. So this part we have to consider first. So let us consider a pipe open at one end and close at other end. Let's see the vibration of air column for a pipe open at this end, close at this end. How it get vibrate, that we have to see. So let's start with this. So according to the book, there is figure 6.9a, 6.9b and 6.9c. So I have drawn this as 6.9a. Okay, this is 6.9a I have drawn. So accordingly, just I will draw all three diagrams first, then we will go further. So first of all, it is better to draw the three diagrams, then we will go further. So let us draw the first one. This is the first pipe close end. This is the open end. Let us consider the second pipe, same pipe here, close at one end and open at other end. So this is another pipe, same pipe actually, not another one, same pipe. This second diagram I have drawn. Let us draw the third one. So let us draw the third one. So you can draw here the third diagram. Did you got it? Yes, you are going to see it. So these are the third diagram of the same pipe, close at one end, open at both ends. Okay. So here three diagrams or three conditions we are going to consider. So suppose the first diagram is there. So here the antinode gets formed and it travel to the bottom. It can travel to the bottom just like a wave it is now. So it goes like this curved part. So it is again the curved part. So this is nothing but an incident wave. This is nothing but a reflected wave. This is the node, zero intensity, antinode, maximum intensity. Let's go to second diagram as they have drawn in your book. So it is what? So again antinode get formed here. So it gets formed here like this. So I will draw it merged with the, basically it merged with the wave-like structure. So such part. Then what will occur? It goes down like this. It again goes down like this. So this is second diagram they have drawn. This is node, again the node, antinode and antinode. So what get occurred here? In this case, the first diagram is suppose A, second is B, and third is C. In first diagram, only one node and one antinode get formed. Second diagram, you must draw it well. I have not drawn that much well here. Just look at the book, you must draw it well as according to the book. So second diagram, in this case the two nodes and two antinodes are here. In the third case, there are what? Three nodes and three antinodes. So let us draw it like here. So here I have drawn like this. So here first loop get created. So here it goes. It must be smooth actually. It must be smooth like this. Then it goes like this. Then it goes like this. Again I have drawn it for sake of your understanding. You should draw the diagram according to book. So two nodes, two antinodes, three nodes, 1, 2, 3. Three antinodes, 1, 2 and 3. That is nothing but a figure C. In this fashion we have drawn the three figures. Now here, before going into nomenclature of this, first of all just see here. Suppose I have drawn one single wave like this. Single wave I have drawn like this. The length of the single wave is what? It is wavelength of the wave, that is lambda, that we have learned in 11th standard. Instead of drawing it horizontal, suppose I have drawn it vertical like this. Positive part and this is the negative part. This length is what? Wavelength represents. Same wave I have just rotated vertically. So it is wavelength lambda. Is that clear? Now see the first case. Here this part is nothing but what? 1/4 of the wave. As we are going here, just we can say this part is nothing but what? This 1/4 up to this part is here. The case node is here, node, it goes higher, it is antinode. So it is antinode, here node, this part. What is the length of this part? It is lambda by 4. It is lambda by 4, and that's why in your book they have shown here L equal to lambda divided by 4. L equal to lambda, total is lambda, here it is lambda by 2, here it is lambda by 4, so it is lambda by 4, that they have shown here. Second diagram, what they have done, they have just drawn here L equal to, second diagram, what is this? This is half wave, half plus 1 by 4. So see, half plus 1 by 4 up to this from this total distance. How much is the distance? This lambda by 2 plus lambda by 4. So let's draw here. This distance is nothing but what? Here I will write lambda by 2 plus lambda by 4. Okay, 4 plus 2, 6 lambda by 8. 6 lambda by 8. 2 3 are 3 by 4 lambda. Just divide by 2. 2 3s are 6, 2 4s are 8. So 3 by 4 lambda. So that we can write here 3 by 4 lambda. Suppose it is lambda 1, suppose it is L1. It is L we have considered, lambda we have considered. So it is L1 lambda 1 that we get here. Let's go further. The last diagram if we see here, how many wave? So if we start here, it goes down and completed here. So this much distance is what? Lambda plus this is what? Lambda by 4. So single wave get created here. So this from this point to this point is lambda plus lambda by 4. So what we get here? Lambda plus lambda by 4, that is nothing but that length. Draw it, lambda plus lambda by 4. So 4 plus 1, 5 lambda by 4 is the distance. And suppose that length was represented by the another alphabet, it is L2 equal to 5 by 4 lambda 2 suppose. 5 by 4 lambda 2 suppose. So this is the thing that from this 3 diagram just we have to consider according to book. Let's start with the first mode or the fundamental mode of vibration here. First, then the second fundamental mode, or sometime it is said to be 0th mode of vibration, where the figure A we have to consider. So let's start with these 3 modes here now. Let's start with the first mode for the first figure, for this figure A. For figure A, the first mode, it is A suppose. For figure A, what we can write here? L equal to lambda by 4. This implies that lambda equal to 4L. Simple concept it is, lambda equal to 4L. As we know one formula that already we have derived in 11th standard, which gives the relation between velocity of the wave, frequency of the wave and wavelength of the wave. If you remember, V equal to N lambda. N is the frequency, lambda is a wavelength and V is a velocity. Just put the value of, suppose if we put the value of lambda here, or either from this equation find out N. We are interested in fundamental frequencies, harmonic and overtone. So we are interested in frequency. Find out N. N equal to V by lambda. So it is V divided by lambda. N equal to V divided by lambda. In this case, what is the value of lambda? 4L. Put it here. We can write N equal to V divided by 4L. So this is said to be fundamental frequency. First frequency, basic frequency, fundamental frequency, or it is said to be 0th harmonic, or it is said to be first harmonic. fundamental frequency, or it is said to be, just see what they have mentioned, known as first harmonic or fundamental frequency. This is said to be first harmonic or fundamental frequency. First harmonic or fundamental frequency. Let's suppose this equation 1. This is for figure A, or equation A, you can say A according to figure A. Similarly, you can consider the second case, it is B, for figure B, first mode of vibration. This is for fundamental mode of vibration. Now let's go for first mode of vibration. Now let's see this second diagram. In this second diagram, what is L1 equal to 3 by 4 lambda 1? Write down here. L1 equal to 3 by 4 lambda 1. This implies that lambda 1 equal to 4 L1 by 3. 4 L1 by 3. Or simply you can put this as L according to book. Don't take L1 L2. Let's take it as L only. Just take lambda 1. So lambda 1 equal to 4 L by 3. So we get this lambda 1. As we know the equation n equal to V divided by lambda. Put as here n equal to V by lambda, that is the basic equation. But this is first mode, so it is n1, it is lambda 1. Put the value here, you can write V divided by 4 L divided by 3. What it comes to be? 3 by 4. You can write this as a 3 into V by 4L, it is N1. Just take this 3 goes to numerator, 4 remains same. So V by 4L into 3. Now just see the figure, so equation A. V by 4L is what? N. So this V by 4 is N. So just put it here. You can write N1 equal to thrice of N. So this is the equation B for second figure B. This is equation B for second figure B. What does it shows? It is first harmonic. It is first harmonic or fundamental frequency. It is said to be, this is first overtone and third harmonic. Remember, it is said to be first overtone and third harmonic. Let us confirm it from your book. This frequency is third harmonic, or it is said to be first overtone. Say the N1. So it is first harmonic, first overtone, first higher frequency than the fundamental. First overtone, as 3 comes here, it is said to be third harmonic. So this is nothing but what? First overtone and third harmonic, as we have just seen according to the figure B. Let's go for figure C. I will write here. Did you got it? Yes, you are going to see it. Yes, you can, na? Yes, you can. So let's start with this. So what will occur here in case of figure C? For a figure C, just look at the figure C first. If we see this figure C, what is L equal to? 5 by 4 lambda 2. Just use that value here. L equal to 5 by 4 lambda 2 for figure C. Just this equation implies that lambda 2 equal to 4 by 5 L or 4L by 5. Is that? Yes, that is very simple. As we know the formula, n equal to V by lambda. It is second, so it is n2 equal to V by lambda 2. Put this lambda 2 here. You can write it as V divided by 4L by 5. So you can write this as 5 goes to numerator, 5 into V by 4L, that is nothing but a n2 equal to. Again from figure A or equation A, n equal to V by 4L. So this is nothing but a n. So you can write as 5 into n, that n2 equal to. From this it says that what is this? Second overtone. Second overtone and fifth harmonic. Now might be you consider the words we have used when we have seen the definition of harmonics and overtone. There they have used one word. Harmonic may be present in the sound, may not be present in the sound, but overtones are always present in the sound. What is the meaning of this? See, it is first harmonic, then directly third harmonic. Where is the second? Second is absent. Third, fourth is absent. Now direct there is a fifth harmonic. So here only first, third, fifth, next 7, next 9, 11. That means all odd harmonics are present. That's why I have used the word odd and as well as even harmonic. So remember, all harmonic may be present, may not be present. Here only the odd harmonics are present. But what about overtone? First harmonic, fundamental frequency. This is a first overtone. First frequency higher than the fundamental. First overtone. Second frequency higher than the fundamental. Second overtone. Next would be third overtone. Means all overtones are always exist. But harmonic may be, may not be. Is that clear? So simple thing is this. Just remember, you can draw these three equations for these three figures. And that you have drawn from simple formula that we have to consider this value of L. L, L. Just put the value and find out lambda 1, lambda 2. Put in the formula this and find out the fundamental frequency and basic higher N1, next higher N2, next higher N3. In this fashion, you can derive the equation. In general, you can say for pth overtone, we can write here equation NP. P is what? Just see, first harmonic, second harmonic, so on up to nth harmonic. Sorry, pth harmonic. NP equal to what? Here it is 5, 3, 5. So you can write here 2p plus 1 into fundamental frequency. Let's confirm it from your book. 2p plus 1 they have taken or something else they have taken, that we have to consider. So it is 2p plus 1 into n, where p varies from, it is 1, 2, 3, so on up to last 1, where p varies from p equal to, it should be 1, 2, 3, so on. So if it is, suppose, or p equal to 0 also you can take here. 0 also you can take. If p is 0, 0 into 2 is 0, so it is 1, n. So 0, n0 equal to n. That is this original frequency, n0, fundamental frequency. Put p equal to 1. 2 into 1, 2 plus 1, thrice n. So that is thrice n. As we have put it 1, so n1 equal to thrice n. Next, n2 equal to 5n. In this fashion, in general, pth overtone is 2p plus 1th harmonic. So this is what? Overtone, and this is what? Harmonic. Pth overtone is 2p plus 1th harmonic. So this is nothing but a basic part we have learned. Apart from this, one topic is remaining, little bit some modification. This topic is over. But what is the difference between this topic I have taught you here on the blackboard and the topic they have given in your book? There is nothing special. Just they have just put the value of capital L. As this is a pipe closed at one end, open at other end, it has end correction at this top only. Here it is E, end correction. And this is the length of this is small l. So the total L is what? In this case, total L is what? I will write here. Total L here. L equal to small l plus E. L equal to small l plus E. You can put this value here. L equal to small l plus E. So here in this equation, you can modify this. You can write like this. Equal to V divided by 4. Capital L means what? Small l plus E. That's it. This is the modification in fundamental frequency. Same way, whenever there is L here, you can write this as 3 into V divided by 4 small l plus E. Same here. In this case also, you can write the same as here. You can write as V 5 into V divided by 4 into small l plus E. That is only the difference, and that is minor one. So you should consider this. So this is nothing but a vibration of air column for a pipe, vibration of air column for a pipe open at one end and close at other end. I hope you got this topic. Let's go to next one. Next one is what? Exactly similar. This is the pipe, open at one end, close at other end. Now next would be what? Vibration of air column for a pipe open at both the end. Okay, I hope you can derive that equations also. It's very simple. That equation is also very simple. Little bit modification is there. So what are the modification? Let's have a look over that. So again we have to consider this pipe. Second thing, to pipe open at both the end. Open at both end. As boundary condition get changed. What are the boundary conditions says? Boundary condition says that antinode is always formed at open end and node is always formed at close end. Now see, when we consider the pipe open at both end, what does it means? The pipe has open from both sides, so it means that it has both antinode at the top as well as at the bottom. At the top as well as at the bottom, pipe has only the antinodes. So let's go to the next. If you see the figure 6.10 A, B and C, that figure we have to draw. Let's draw it here. I will try to draw it. Suppose this is the first pipe. First diagram of the pipe just I have drawn. First diagram of the pipe I have drawn. Let's see, suppose this first. Similar to last one, let us draw the three diagrams. So this would be the second one, and let's go to the last. This would be the third one. So these are the figure A, figure B, figure C. A, B, C I have drawn. Now let's see, according to condition, boundary condition, antinode is always formed at open end. As the pipe is open at both end, so here antinode get formed at this end and this end. So it becomes like this. So this is antinode, this is antinode, this is node. That is a first condition or first figure A. Now here this is lambda by 4. This again lambda by 4. What is L? L equal to lambda by 4 plus lambda by 4. It is lambda by 2. It is lambda by 2. So it has two antinodes and one node. Let's go to next. 3 antinode, 2 nodes. Figure B. So let us draw it like this. Suppose I have drawn it like this. So this is the second figure. Okay, 3 antinodes. 1, 2, 3 antinodes and 2 nodes. What is the length nowadays? This length must be what? It is L equal to, see, this is lambda by 2, half part. And this lambda by 4 is lambda by 2. Lambda by 2 plus lambda by 2, it is lambda. So L equal to lambda 1. It is 1 for second diagram. Let's go for third. In that third diagram, little bit modification you have to draw, the little bit reflection. Let's see what exactly the third diagram is. So might be reflection get reduced, not that much get reduced. Little bit again. Yes, I hope it get reduced now. A little bit it get reduced. Okay, let us draw the third diagram. Third diagram consists of 4 antinode, 3 nodes. 4 antinodes and 3 nodes. So let us draw it like this. So 4 means what? 2 loops we have to draw. Let us draw the 2 loops like this. So this is the first antinode, second antinode, third antinode, fourth antinode. Try to draw this diagram. You must practice yourself so that you get a better diagram here. I have not drawn the better one. Still you can try the better one. Okay. So just I will write it like this. So try to draw the better diagram. Okay, than me. So it has 4 antinode and 3 nodes. 1, 2, 3. That is the third diagram. What is the value of lambda again here? So see, the one wave gets start here. It comes here and complete here. So this is lambda, one wave. positive and negative. Lambda plus lambda by 2, lambda by 4 plus lambda by 4 is lambda by 2. Lambda plus lambda by 2, it becomes thrice lambda by 2. So it becomes L equal to 3 lambda 2 divided by 2. So we get these three conditions. Now here as usual we have learned that we have to derive the equation. So accordingly, let's go to equations now. Let's start with the figure A. First, for figure A, what we can write? Write down L equal to lambda by 2. As L equal to lambda by 2, this implies that lambda equal to twice L. And we know N equal to V by lambda is equal to what? V by twice L. N equal to V by twice L. Now capital L is what? This diagram we can modify. This length of the pipe is what? Small l. End correction at the top, E. End correction at the bottom, again E. So what is total length? Capital L equal to small l plus twice E. That is a modification only. So put it here. V divided by 2 in the bracket L plus twice E. This is the equation A. This is the equation A. And that is nothing but what? Fundamental frequency. It is said to be fundamental frequency, or it is said to be first harmonic for a air column, for a pipe open at both ends. I hope you can got this. Nothing to explain. It is similar to first one. Let's go to second diagram. From the second diagram, we have to consider the length L equal to lambda 1. Just do it the same for second diagram B. For figure B. Figure B means what? When the two figure B means what? When the two nodes and three antinodes are formed, that is said to be figure B. That is said to be figure B. Similarly here we have drawn it. Okay. Remember, figure B means what? It is nothing but what? It consists of how many antinode? 3 antinodes, 1, 2 and 3, and 2 nodes, 1 and 2. That is nothing but a condition for figure B. So similarly, from that we can write as L equal to lambda 1, and we know N equal to V by lambda. It is for fundamental. This is the first higher. So just you must use little bit different way. Hello. So what we have seen for figure B, as we have just written L equal to lambda 1. As we know, N equal to V by lambda, but it is not a first frequency because first is this fundamental. So here it should be N1 equal to V divided by lambda 1. Put the value of lambda 1 here. Put the value of lambda 1 here. We can write here V divided by L. Okay. V divided by L. Multiply and divide here right hand side by 2. So you can write N1 equal to 2 into V divided by twice L. If we consider these two get cancelled out, we get V by L. Now compare this with equation 1. V by twice L is what? N. So you can write this as equal to twice N. N1 equal to twice N, or you can just modify it accordingly, equal to twice into V divided by 2. Capital L is nothing but small l plus twice E. Okay, just we have put this value. This value we have kept it here. That's it. So from this you can say this is what? First harmonic. Not a harmonic. It is what? Overtone to left side, harmonic to right side. So it is first overtone and second harmonic. First overtone and second harmonic. So that is said to be first overtone and second harmonic. Let's go to third diagram. From the third diagram, what we can write here? L equal to 3 lambda 2 by 2. So just put it here. L equal to, so it is for C, L equal to 3 lambda 2 by 2. That is for figure C. For figure C means what? For this figure where 4 antinodes are formed. 1, 2, 3, 4, and 3 nodes are formed. 1, 2, 3 nodes are formed. For that figure, we are going to draw it here. So let's draw it here. So as we know, the thing that so L equal to thrice lambda by 2 here we have drawn. Now just find out the value of lambda 2. So this equation implies that lambda 2 equal to 2 by 3 L. 2 by 3 L. And as we know, n equal to V divided by lambda. It is second higher frequency. So it is n2 equal to V divided by lambda 2. V divided by lambda 2. So you can write this as V divided by twice L divided by 3. Solve it. 3 goes upward. V divided by twice L. That is n2. So same thing can be written as 3 into V divided by twice small l plus 2e. So that is nothing but a end correction. So as we know, V divided by twice l from equation A, it is nothing but what? It is n. So you can write this n2 equal to thrice of n. From this is what? Second overtone, and that is said to be third harmonic. Second overtone and third harmonic. As you see, in this case, when a pipe is open at both ends, so see, the first harmonic is there, second harmonic is also there, second harmonic, third harmonic is also there. What does it means? All harmonics are present for a pipe open at both ends. Even as well as odd harmonics are present, or we can say integral multiple of fundamental higher frequencies are present. That is said to be in vibration of air column in a pipe open at both ends, all harmonics are present, and this is the reason why the quality of the sound wave or sound wave produced in this case of pipe open at both ends is melodious and very clear as compared to pipe open at one end and close at other end, because here all harmonics are present. In case of pipe open at one end, close at other end, only odd harmonics are present. That's why less frequencies, quality is less. So very nice quality sound we get here in case of pipe open at both end. Now apart from this, if you consider here in the same manner, if you go as we have seen in last page, so it is, suppose we have taken pth overtone NP. Pth overtone must be equal to what? 2m plus 1 harmonic, means it is n. Or 2, what they have used in your book, that symbol will use. So what they have used? 2p plus 1, as they have used in case of pipe open at one end, close at other end. Let's go for this. For this, what the symbol they have used? It is simply the p plus 1, because it is all harmonics are present. There is no need for 2m or 2p. P plus 1. So pth overtone is p plus 1th harmonic. Okay. So if p equal to 0, it is fundamental frequency. N0 equal to n. Original frequency, fundamental frequency. P equal to 1, 1 plus 1. P1, N1 equal to twice n. This is the case. P equal to 2, 2 plus 1, thrice n. So N2 equal to thrice n, and so on. In this fashion, all harmonics are present here. So you can see this is the part we have learned up till now. Afterward, there is some conditions or there is some comparison. Just see on page number 144, right hand side at the top, they have, it may be noted that in your book they have mentioned sound produced by an open pipe contain all harmonic. Open at both ends contain all harmonic. That already I have told you. Its quality is richer than produced by the pipe closed at one end. That already I have told you. Second, fundamental frequency of vibration of air column in a pipe open at both end is double of that of frequency in same length pipe for a closed pipe. What does it mean? Fundamental frequency they have just compared. This is the equation for fundamental frequency for a air column for a pipe open at both ends. So this open. So this is frequency NO, open at both ends. Initially, if you remember, we have derived the equation n equal to V by 4L. equal to V divided by 4L plus E, if you remember. If you equate, this is for closed pipe NC. Okay, so NO equal to twice of NC. You can derive this equation from these two equations. Try to solve it. Just put the values, solve them, and find out the relation. You get this equation. So the frequency of pipe open at both end double that of the pipe open at one end and close at other end. Apart from this, in your book, there is little bit some calculations they have shown for end correction or determination. They have just derived some next topic, simple formulae, mathematical formulae they have used, that we have to use. The two formulas for two. One, pipe open at both end. This is the first. Second, pipe close at one end and open at other end. So these are the two cases that already we have learned. Now here in this case we have to see the two conditions as they know. As we know in case of pipe open at both ends, now just we have derived n equal to V by twice L. Here it is n equal to V by 4L, if you remember. This part we have learned. Just we have derived this equation, fundamental frequency or first harmonic in both the cases. That part already we have learned. Now here, find out the value of V from this. V equal to what? N into twice, or you can write just directly twice NL. Capital L it is. Twice NL. Okay. Suppose it is twice NL. So suppose it is twice NL from one pipe. Second pipe it remains same if the length is same. So same way you can write here simple equation as V equal to twice N1 L1 equal to twice N2 L2 for second. First frequency, this is for first frequency, this is for second frequency. Same way you can write here V equal to 4 N1 L1 equal to 4 N2 L2. So we can write this as 4 N1 L1 equal to 4 N2 L2. Similarly, this implies that twice N1 L1 equal to twice N2 L2. So simple equation we have written here. So apart from this, just we can put the value of L1 for it. L1 means here the total length. As here the two corrections, because pipe is open at both ends. So you should write this capital L as twice N1 in the bracket L plus twice E. L plus twice E. And it is L1, so it is L1 equal to twice N2 in the bracket L2 plus twice E. Is that clear? We have put the end correction also. So here we get these equations. So N1 L1 plus twice E equal to N2 L2 plus twice E. From this just transfer the term left side, right side. Just do the common, take the common term and find the value of E from this. I hope you can find this value of E. Is it? Can you? Okay, fine. I will solve it. Just multiply these two bracket, multiply these two bracket. You get 2N1 L1 plus 2N1 into twice E equal to twice N2 L2 plus twice N2 into twice E. These things you can write like this. Now our aim is find the value of E. So to find the value of E, just take E term common. Okay, this is E term, this contains the E term. So just we can write simple thing. Move this term to that side, move this term to this side. What we get? Twice, here is 2, here is 2. Take it common. N1 L1 minus N2 L2. This we have drawn. That term comes here, it becomes minus. Equal to, what is that? Twice is common. N2 into twice E minus twice is common N1 into twice E. So this thing we get. Okay. So here actually N1, N2 here there comes. So just find out twice E. E, our aim is to find the value of E na. So instead of taking 2 common, take E common. So you can write this 2 E also. So this E goes because we have taken common. So we get like this. N2 into 2, N1 into 2. So you can write it write like this. So same thing you can write another way. E equal to, this implies that E, this 2 from this side, 2 from this side cancelled out. Again this 2, take it outside. So you can write this as 2, this 2 goes, this 2 goes, because that we have taken common. Now just find out the value of E. We get N1 L1 minus N2 L2 divide by this 2 goes denominator in the bracket N2 minus N1, and this is the value of E, end correction for a pipe open at both end. Similarly, N2 minus N1 is here, and here N1 L1 minus N2 L2. If you swap this term, you get the second equation. So you can just swap this numerator and denominator. So minus minus get cancelled out. So you can write this as, take this first, N2 L2 minus N1 L1 with a minus sign, divide by minus sign twice of N1 minus N2. Minus minus becomes plus. The same equation in different form we have drawn. Both the equations are same and both the equations give the end correction. This is for a pipe open at one end and close at other end. Just look at it like this. Little bit reflection is coming, that's why I am showing you like this. So this way we have derived this equation. Same thing they have shown in your book for a pipe open at both ends. Same way you can derive the same equations. Same way you can derive the same equation for pipe open at one end, close at other end. Only difference is what? Here twice E we have taken, here it should be only the E. I hope you can do this. Try to solve it. Try to solve it at your home. This homework today to you. I know that those who have mathematics, they can do it easily. Because simple mathematics basically. Those who don't have mathematics, don't worry. This is simple thing. Just solve. Put here L1 equal to L plus E. So you can write 4N1 L1 plus E equal to 4N2 L2 plus E. Solve it. Take a common term. Just find out the value of E. Definitely you get. Those who have mathematics, they will definitely got it. Those who don't have mathematics, they 101% got it. Little bit they require much more effort than the mathematics students, but do it. So this is homework to all of you. Below that, remember this. There is one point. Remember this. What we have to remember: for correct value of end correction, the inner diameter of a pipe, the inner diameter of the pipe, inner diameter. So if you remember, end correction we have written E equal to 0.3 into D. This D is inner diameter. For correct correction or for correct value of end correction, the inner diameter of the tube must be, or of the pipe must be uniform throughout. Pipe must be uniform. Suppose at the top it is small, at the bottom it is large. That is not possible. Then the correction get decreased, that correction get changed, and that is useless for us. So the pipe must be uniform internally. Inner diameter must be uniform. It may be noted that effect of flow of air and effect of temperature of air outside the tube has been neglected. See, we have taken, suppose this is pipe, okay, uniform pipe. Outside, this is the air is flowing. So that air, flow of air we have neglected. Apart from this, outside the pipe, temperature may be little bit differ. Inside the pipe, whatever be the air, temperature may get little bit differ. So that temperature difference also we have neglected while calculating this end correction. I hope you got this. Apart from this, there is one activity they have shown. What is that activity? That we have to see that activity, and after that activity, just we have to see what activity means. That activity is what? Application of this, whatever we have learned up till now, that application based activity is there, and from that activity you can find out the velocity of sound at room temperature. By using this concept that we have learned, pipe open at both end, pipe open at one and close at other end, you can find the velocity of sound wave at that time anywhere on the Earth's surface at that time, at that temperature, you can find out the velocity of the particle, or sorry, velocity of sound wave at that time, at that place. So you have to just read it. We have to perform this practical in our lab. So it's again activity. Again, I am going to give the homework to all of you.